On to the next session, Immersive Data Technology. My name is Brian Anthony. I'm the director of the Immersion Lab, the associate director of MIT.nano. Immersive data technology. I think of us, we're at the top of the technology stack. So we think about and facilitate work that has the human immersed between hardware, data, and experience. So hardware meaning compute and sensors, data meaning data and the information that we get out of data, and the human experience. And that could be either the person that needs to work inside of MIT.nano or the person that needs to learn how to use an instrument, or the person becomes a specimen we observe them as they interact with technology. So what is the Immersion Lab? It's the third pillar within MIT.nano. Oop, that's not advancing. Does that advance? One of these will advance. That one advances. There we go. So this is the Immersion Lab, the space. So we 3D scan the space. We see a bunch of cameras inside of there where a person can stand in there, and we can do motion capture. But this is the Immersion Lab. This is a flamenco dancer that has markers on his body, and the cameras around the Immersion Lab are capturing his motion in 3D space. We have wireless physiological sensors that are monitoring his heart rate and his respiration rate. We have accelerometers on the floor that are monitoring as his feet interact. We'll see the data here in a second. We see the camera crew watching him, but we see the 3D points that are being tracked. A little bit, we'll see all the wireless signals that are being transmitted from his muscle activation, his heart rate, his respiration rate, and then the floor signals, so that we can understand how he interacts with the floor. So that's one example of being immersed between hardware and data and experience. We're trying to understand, well, what does it mean to be a professional expert dancer? What can we learn by studying the motion, the kinematics, the body, the way that the body responds? The Immersion Lab supports multiple communities. We support the human experience, both quantified and subjective, the intersection between art, and that can be dance. It can be, well, how do we use immersive technologies? That can be AR and VR. That can be things like motion tracking. That can be things like head-mounted displays to be able to rapidly visualize how you're interacting with your physical objects or your virtual objects. It can be rapidly spinning up high-performance compute. So I can not just do machine learning on that wonderful cryo-electron microscope data that I'm imaging, but I can sort of rapidly spin up, rapidly in real time manipulate it, and not just wait for a computer to give me an answer after several minutes, but what do I actively do with my data to understand it and to manipulate it? So again, the intersection, the immersion between hardware and data and experience. So the tools that we have, ability to do motion capture, ability to do wireless physiological monitoring, wearable or immersed in the environment, cameras on the wall, radar sensors in the ceiling, accelerometers on the floor. The language and tools of gaming, AR and VR, compute, GPUs, virtual environments, and then take the approach of the artist, the approach of the scientist and engineer, and the approach of the clinician. And we bring these things together to really try to form little special interest groups with industry communities that are interested in, say, healthcare, sports, and digital therapeutics, and trying to say, well, what collectively is the market opportunity for these types of immersive technologies in that space, or within design and manufacturing, collaborative design, or how do we use these tools on the factory floor to better monitor the person or to better interact with the technology that we have to rapidly open the manual for to figure out how we debug. And then the tools and technologies, whether it be the sensors that are allowing us to monitor the world, both the human and the environments, the built and natural world, and how do we use these tools for education and research. And then how do we use these tools, what does it mean to quantify and to improve the artist? So today, to try to celebrate the users, the community of people that think about immersion-like technologies being at the intersection between hardware and data and experience. We'll have three speakers that talk a little bit about the hardware. So Juejun will speak first about hardware. Then Deirdre Logan will speak a little bit about medicine applications. And then we'll close it up with the opera for the day and talking a little bit about opera with Scheib. Again, celebrating the various communities that we support within the Immersion Lab and how we use everything from the novel sensors and novel electronics that are being developed and researched within inside of Nano. get them up to the human scale and interact with them in ways that are changing the way that we think about applications and uses. So with that, I will first invite JJ to come up, and then we'll go through a series of talks, and we'll take some questions at the end. JJ, take it away.
Thank you so much. Okay, thank you for the introduction. So it's certainly my privilege here to address this audience to discuss some of our work in the area of hardware, especially for immersive technologies. So because we are talking about emergent technologies here, let me start by talking about state-of-the-art AR/VR modules. So what I'm showing you here, this is actually a Meta Quest Pro, which of course is a very powerful AR/VR kind of headset. But what a lot of you probably have not realized is that on these modules, there are actually a ton of sensors that are actually integrated. If you count it, there are actually a total of 13 imaging-based monochromatic sensors that are integrated on the headset, on the handset, okay? Performing a wide array of functions ranging from head tracking, depth sensing, eye tracking, hand tracking, all those different functionalities, okay? Now, one thing I have emphasized here is that these are actually monochromatic sensors, meaning that they actually have active illumination source, typically to LED or laser. You then use a single color camera to then capture the reflected image and then give you the desired information. The challenge, however, though, is that with this kind of sensors, currently optics can be one of the major bottlenecks. So what I'm showing on the left-hand side here is actually sort of a dissection of one of these kind of sensors people use currently in consumer electronic devices. And you can clearly see that if you look at the optic side, it requires multiple stacked refractive elements, just so you can actually suppress optical aberration. And this, of course, increases the complexity of the raw system, increases volume, also the overall cost. So what we are trying to do here is we are looking for ways to potentially break this kind of trade-off and then enhance the performance while also giving a more compact footprint at the low cost. So the technology solution we are coming up here is essentially called optical meta surfaces. And to introduce how it actually works, let's step back a little bit, take a look at how the conventional lens operates. So if you look at conventional lens here, essentially you have lens coming in here, and by having this kind of curved geometric surface, you can then bend the appropriate direction of light to actually focus it. The other way to look at it is to think of it as a device that actually introducing a spatially dependent optical phase delay. Because in the center here, the light has to go through a slab of material with high refractive index, which will reduce more phase delay. So in the end, you essentially can bend the wavefront of light, and then eventually, this then creates a converging light ray that focuses on the focal spot. Now, meta surfaces actually operate under exactly the same principle here. What we have is basically a set of microscopically fabricated structures on a flat, transparent substrate. And by engineering the size and shape of these sub-wavelength scale structures, you will then be able to impart a phase delay depending on its specific locations. Now, if the size of these features is actually much smaller than wavelength, then the instant light will not be able to tell the difference between this kind of a staircase-like phase profile and a conventional continuous phase profile. And what you end up getting here is basically the meta surface lens, or meta lens. So the first challenge we want to tackle here is that can we actually use a meta lens to actually simplify optical design, to reduce the many optical elements into maybe one single optical element. So one case in point here is actually so-called fisheye lens. So for those of you who are familiar with photography, it's a kind of lens that allows you to capture very wide angle images, right, up to like 180 degrees. However, to get that, you typically need to stack somewhere between 10 to 12 individual lens elements, which of course makes it very complicated and difficult to assemble. So a few years back, we actually come up with a way to actually transform a flat piece of thin glass into a fisheye lens that can capture 180-degree panoramic images with a very high optical quality. So this is sort of, excuse me, let me see how to go back here. Okay, so what I'm showing on the left here, this is essentially the architecture of the lens. So we have a piece of transparent substrate. On the front side, we have an aperture. When light comes in at different angles, it will refract at the front surface and then go to a back side where we engrave this kind of microstructures or the meta surfaces. What we have shown is that if you design the meta surface properly, then all the light can get properly focused into a flat image plane with very high quality. So on the right side, this was actually our first prototype we actually demonstrated in the lab. And as you can see here, this is actually a measure of focal spot profiles. So at 0 degrees, you see a nice sharp focal spot. And if you go all the way to 85-degree incident angle, this is when the light comes almost parallel to the surface of lens, you can still get this very nice sharp focal spot. So takeaway message here is that we now have a technology that can offer ultra-wide field of view, very high resolution. We have proven experimentally that this can actually be diffraction limited, which is sort of a theoretical limit you can get with this kind of lenses. And you can also manufacture them at scale and low cost using a standard CMOS microfabrication technologies. Now, just to show you that the last statement I'm making here is not just a statement on paper. Over the past few years, we have worked very hard with our foundry partners to realize scalable fabrication of these kind of metal lenses, now on big wafers. So what I'm showing you here, this is actually a picture, shows an 8-inch glass wafer with a whole array of this metal surface fabricated. You can see this very nice quality here using essentially a silicon on glass technology. Okay? And if you want to look at the performance here, we can then integrate one of these metal lenses on top of a commercial off-the-shelf CMOS image sensor to form essentially a fisheye metal surface camera. Now, if you position the camera here to actually image this semicircular target, this is what you're going to get. So as you can see from this image here, we can actually achieve, in this case, very close to 180-degree field of view, about 170 degrees. And you may notice that the image does show some distortion at the edge, which is quite characteristic of any kind of fisheye lens, right? Because you're trying to map essentially a hemispheric field of view into a flat surface. So inevitably, at the edge of the field, you have to introduce some kind of distortions. However, the key point here is that despite the distortion, we can get very nice and sharp images, both in the center of the field and at the edge of the field. Okay, so resolution is not getting compromised by the distortion. And we have also proven, as I said, that we were able to actually achieve diffraction limited performance across the entire near 180-degree field of view. So now what can we do with this kind of a metal surface wide field of view lens technology? So I'll give you a few examples here. The first example is that we can actually use it to create a stereo camera. So essentially, by positioning two of these lenses together side by side, and through triangulation, we can not only get the shape of the surrounding objects, but also their depths or distances. So in this demonstration here, we basically put a little pumpkin there, which is, of course, is a very timely experiment given that Halloween is right around the corner. And what we can see here is that through our algorithm, we can actually capture not only the images of the pumpkin, but also like how far away it is actually from the camera. So another example I want to mention here is that we can also realize essentially a zoom lens. And this is actually useful because despite that people want the wide field of view lenses to look at overall scene, sometimes you also want to be able to zoom in and look at a specific section with much higher resolution. Conventionally, this is done essentially using a mechanical moving parts. You have a little lens element that actually translates with respect to other elements here to get a mechanical zoom. And this, of course, complicates the overall system setup and also decreases its robustness. So in our case here, we can actually use metal surface technology to realize optical zoom lens without any mechanical moving parts. So what we are using here is we're taking all the advantage that these metal surfaces can actually be designed to be sensitive to the instant light polarization. So with the two orthogonal polarizations, we can actually encode two different optical designs into the metal surface here to realize two different optical zooms. So the specific design is illustrated here. So in one design here, you essentially have a lens that essentially diverges instant light and then focuses it using the second surface. In the second configuration here, or the second polarization, the two lenses essentially switch roles to give you essentially a much higher resolution in this case. So from the experimental results, you can clearly see that we were actually able to realize 10x optical zoom, which is consistent with our design. And you can see this is actually a wide-angle view, give you the overall image. And here you can zoom in and see much more the details with much higher resolution. And by integrating a polarizer, a kind of a checkerboard type of a chip scale polarizer directly onto image sensor, we can actually capture both images simultaneously onto one image sensor without having to introducing any mechanical moving parts. So last thing I want to mention here is that this is about a different technique to actually enable 3D depth sensing. So previously, I talked about stereoscopy, okay, which is nice. You can obtain the depths of objects, but actually requires always two different cameras juxtaposed with each other, okay? And this brings the issue that if you want to accurate triangulation, you need to have some spacing between these two optical apertures here. So that brings a trade-off between the accuracy as well as the footprint of the overall system. So it becomes desirable to see if you can actually use one single lens or one single optical aperture to capture not just the scene, but also the depth information. So we were actually able to do that. I'm not going to go into much of the technical details, but the whole idea is actually you can actually engineer the focal spot of the lens so that the focal spot shape not only depends on the polarization, but also depends on the depth or distance of the object. Now, more specifically, you can look at these two examples here. This actually corresponds to two orthogonal polarizations that we are actually imaging using our meta lens. You may notice that this MIT pattern seems to be blurred. That's actually intentional because the focal spot in this case is actually not a single focal spot, but actually two focal spots that actually rotate with each other. And the rotation angle actually depends on the depth or the distance of the object. So by combining both information together and through some post-processing, we're then able to get the distance of these different objects with a fairly high accuracy here. So simply put, what I hope I have convinced you here is that this meta-surface technology can be very versatile. It not only allows you to replace conventional multi-reflected lens elements with a single-piece, robust system, but also at the same time, it can enable advanced functionalities such as optical zoom or 3D depth sensing. So with that, I'm going to conclude my talk here. And of course, I want to acknowledge all my hardworking postdocs, students, as well as employees in the startup company that we work with to actually realize the devices here. I, in particular, want to acknowledge Dr. Tian Gu. He's our optical designers that come up with all these ingenious structures. Dr. Mikhail Shalakinov, Dr. Feng Yang, and Dr. Hong Yiling, they are the actual real heroes that works in the lab day and night to actually realize all of these devices. I also want to thank MIT.nano because a lot of my students and postdocs, they basically live in MIT.nano, especially packaging facility. That's actually the only way to get all this nice work done. So with that, I'm going to conclude my talk, and I'll be happy to take questions. Thank you.
Otherwise, you can hold the questions at the end. So let's take one question, because I know he has to run after this. So if there is a question now, otherwise we'll take him to the end. Okay, there's a question over there, please.
So, can you use these sort of meta lenses to sort of selectively block light, like exactly, like for advanced AR without, like in like full sunlight?
Block the light in what? Could you repeat that? Sorry.
Oh, so can you use these kind of meta lenses for augmented reality that controls all the light coming in, like for example in broad daylight, controlling the light?
So like spectral selective reception. Well, yeah, that's actually possible. I mean, you probably don't even need to use meta lens. You can use essentially like different kind of microstructure optical filters, multi-layer filters to actually realize some of that. And that's actually quite critical if you're trying to design, for example, AR combiners, right? So that's definitely a functionality I think we can realize using the meta surfaces. Yeah. Okay, thank you very much.
Okay, next up. So now we're going to use the technology, and we'll see what some of the novel things are that we can do for our youngest patients.
Hi. So I feel like I am coming at you from a completely different universe, and I'm only hoping that you will understand. Is it this one? Okay. Only hoping you will understand what I have to say better than I have understood what anyone else has been talking about this afternoon. So we'll start with that. We'll see what we can do. I am a pediatric psychologist. I work with children at Boston Children's Hospital. Specifically, I work in our pediatric pain medicine program. So most of my time is with children with chronic pain problems, a whole range of different chronic pain problems that are disabling, that lead these kids to not be able to participate in their normal lives. And we have a whole range of treatment approaches to that, including some very intensive programs where kids are with us for weeks at a time, working with a bunch of disciplines, and that is where this collaboration has come in. So what I hope to talk to you about briefly is a little bit about how we have started to integrate virtual reality into pediatric pain management. I'll talk a bit about a collaboration that we've started across a number of institutions, as well as my collaboration here with the Immersion team. And then I will talk a bit about the actual vision project that I had in mind that brought me here. But my major point really is that this is not work that one can do alone, and the ability to collaborate and access resources such as the Immersion team here has been absolutely instrumental in bringing these kinds of treatments to the kids that we work with. So a few years ago, they assembled a group of experts to kind of take stock of the field of pediatric pain management and think about where it needed to go. And they came up with sort of four goals: making pain understood, making pain visible, making pain matter, and making pain better. And what's striking here is all of the different ways in which technology factors into the vision of pediatric pain management going forward. So you can see all sorts of ways that data and technology is coming into play, and particularly this idea of digital therapeutics. So using things such as virtual and augmented reality applications in the treatment of these problems. All right, and this is really an idea whose time has come. There is now a growing body of evidence to really show us how effective virtual reality can be in the treatment of a variety of pain issues. We know that it's very effective in acute pain settings, so kids who are getting procedures, distressing needle sticks, things like that. It can offer a lot of distraction. Increasingly, we're understanding other ways that it can be used in more chronic pain situations, such as in physical therapy, to help kids engage in movements that are otherwise really challenging, and to kind of address the fear piece of that. In addition to that, these products have become increasingly affordable. So when we started and this was all very expensive, very complicated, it's now affordable, it's portable, we can bring headsets right into almost any clinic setting. There are now a proliferation of healthcare products and companies. Recently, there's the first FDA-approved VR treatment for chronic pain. That's for adults, but we're making progress. When the pandemic hit, VR brought us a way to kind of bring some interventions into the home setting. So these were things we could send some patients home with and extend treatment in that way. And as I said, lots of growing evidence base to really show both the efficacy of these things and also help us start to understand the mechanisms through which VR helps with all of these problems. All right, so then I had this idea, which I'll come back to, about what I wanted to do. And I set out to ask for some funding. And my funders said, well, first you need to go survey the landscape. So go bring everyone together who's doing this kind of work and figure out what's done and how you can all work together. This was a philanthropic funding organization that really liked to foster these kinds of cooperative sorts of things. So that's what I did. I set out to bring this team together. We met in January of 2020. For the longest time, it was like the last time I had been anywhere for like years. So we met, we brought a number of different children's hospitals together, along with, there was some representation from software engineers, there was the philanthropic organization helping us think through how to fund these things. There was another group that, whose mission is to use VR in a whole range of pediatric medical settings, and we had some folks from outside the pain world who also helped us kind of think through what needed to happen to bring this technology into children's hospitals. We also came up with a logo, so it was a good 2-day meeting because we got a great cool title and a logo out of hanging out for 2 days. The turtle is sort of emblematic of how things move in the medical setting when there is a lot of bureaucracy, and the hope is that the VR will get us there faster. So we came up with a number of goals that we as a group wanted to work on. They're very modest. Advance all of our own projects through this network, establish best practices, identify the gaps, develop a repository of resources. We really wanted our sort of high-end institutions to be able to make these products accessible to smaller hospitals, to get these out into the hands of kids who needed them, and we wanted to disseminate the knowledge. So if you're interested, we did generate a paper out of our consortium that you can read about what we hope to do in this field. But that brings me to my project. So here's what I wanted to do. I work, as I said, with kids with chronic pain, and particularly in this intensive program where these kids are with us for several weeks, really working on the goal of returning to function. The biggest area of function for kids is going to school. We have a lot of kids with chronic pain who just flat out stop going to school, or who miss a ton of school because their pain is really getting in the way, or they're there but they're not really mentally engaged. And then we have them in this clinic setting, and we work on going back to school, but it's a little hard because they're in a hospital, and it's not quite the same thing. So the extent to which we can really practice these things has its limits. So what I wanted to do was to use virtual reality to create a simulated school situation that kids could engage in the clinic setting. So this would be a way to address both the physical challenges of school, so for kids who have trouble navigating hallways, kids with headaches who the bright lights are really painful for them, all of those physical pieces, and the psychological pieces. Just the fear of re-entering that situation, the challenges of trying to talk to kids who are asking them questions about where they've been, trying to interact with teachers. All of these things are huge stresses that really create some barriers to school re-entry. So I wanted to be able to address this in a realistic way, and also for it to be something that could be individualized so that every kid could really tackle their challenges in this kind of simulation. I also wanted it to be something where we could be monitoring their physiologic responses and responding to that. So if their heart rate is really up because they're engaged in a really stressful piece of this, there can be some prompting to use some of the strategies that they're learning for coping, and they can employ them in that simulation. And ultimately, hopefully coach patients within that simulation to use the skills that they will bring back to school with them. So again, there needed to be a lot of collaboration because I have a lot of things to do. And I can't do all this, and I'm also very technologically not so savvy. So what's been huge is the collaboration opportunities. I mentioned before, Invinci Kids is a group of actually anesthesiologists who are fairly tech savvy, who have been working to bring VR into a range of pediatric settings, a lot of it around surgical settings, so post-operative, pre-operative kinds of applications. But they had sort of a good sense of the landscape and what was possible in the medical setting. And then the collaboration here with the Immersion team, they've been my go-to people for really realizing this vision. So creating the technology and testing it out. And I will say this is very much a work in progress. I'm going to show you the beginnings of it, but hopefully it's a collaboration that's got a good ways to go as we get to this final product. And then also really helpful to have those other hospitals where people were doing similar kinds of things and we could all kind of bounce our ideas off of each other. All right, so then the other piece of collaboration is really that when you develop something like this, you have your great idea, but you really need to make sure that the patients for whom you're developing this thing are bought into it and also find that it would be useful. So our first step was really to go to patients and talk to them first and foremost about what school was like and what those challenges were. So we made sure we were designing something that really hit the challenges that they're experiencing and also kind of float the idea by them and see what they thought. So we did that through a series of focus groups. It was COVID, so they were all virtual. And we threw out these questions around, what's challenging in school, what was helpful in the program. These were kids who were either in the program when we did it or had finished the program. What else could be helpful? So we ended up with 4 groups of kids from the program. They represent our typical kind of chronic pain demographic in that they're mid-adolescents, they're predominantly female. They've got a range of different pain presentations. And from the information they gave us, we kind of came up with these initial scenarios, most of which we have developed, a few more we're still working on. But the concept of sort of just entering school, navigating the hallways, having to get to their locker and get materials and get to class on time, engaging with peers while they're doing that, and sort of that time piece of it, and then getting into classrooms and really trying to do work, sit at a desk, tolerate that physical environment, talk to teachers, talk to classmates, get through the day. And then importantly, kids really also said, we really need these bigger settings too. We have to have like the stressful cafeteria with all the pushing and shoving, and the gym where we have to like run around and do things. These are really stressful parts of the day. So we're still working on creating some of those other parts of the school day. But these are all scenarios that we plan to expose the kids to through this simulation. So here's some of the work that Brian and Tallis and their team have done so far on some of the scenarios that the kids experience. So that's the entering the school, then they're in the hallway, navigating that piece, they get into the classroom, they have to turn in work and find their desk, and we can sort of integrate these various stressful situations into this. We've done some piloting at this point of this work with 9 patients in our intensive rehab program, and importantly also with a number of clinicians, because that's the other sort of audience for this, is we also want the clinicians to feel like this is a tool that they want to use. So physical therapists, occupational therapists, and the social work and psychology team in our rehab setting all have been involved in giving us feedback on this. So far we've been somewhat wired in the application, as you can see. That looks really complicated and limiting, but the endpoint will not involve all of that. This is really, as I said, a process that we're going through. We did this, the kids went through it, we asked them a lot of open-ended questions and got a little bit of more structured data as well. So you can see, there was a lot of positive feedback. Kids found that this was a realistic situation. It was fairly easy to use. They felt like it addressed goals that they can't otherwise be really working on in this setting. And in our questionnaire measure, their scores suggest a fairly immersive experience. So they really did find that they could buy into this experience, feel like they were really in a school setting. Both clinicians and patients gave us some areas of improvement. So far, the movement is a little wonky to them. We've been using teleportation, and they really want to be able to actually move, and that would help us with some of the physical therapy goals as well. So that's where we're hoping to head with it. They wanted it to be more interactive, meaning that they're really interacting with the other avatars that they're seeing. They wanted more tasks and scenarios, which of course is part of what we're hoping, that it can be sort of varied by level of challenge. So once a kid makes some progress, then that hallway is going to have 50 kids in it, whereas when they're just starting out, maybe there's 5 kids. So that's downstream. They want to be able to increase the stress of the demand. Same thing, we want this to be a progressive kind of experience. And the clinicians really warned us that we also have to think about the space that they could use this tool in. So we have to be a little mindful that they're in a clinical setting, that they only have X amount of space to move around with. We did try to get some former patients to come to the immersion lab to test this out, to see what we could do. And you bump up against sort of the real world of working with humans, and that none of these kids wanted to get to Cambridge. So we had to stick with the clinic, which is probably just as well, because that's where we want to use it. And then in terms of sort of relevance, they all felt it was very relevant to treatment. They talked about the exposure to both physical and psychological triggers, the chance to develop coping strategies, work through some of the challenges. And the clinicians really felt, yes, this is something that can be used across disciplines. We see ways to use this in physical therapy as well as in psychology. So we've written up a little bit of that, mostly focusing on those initial stages of getting the information from the patients. And we hope to also look at some of the physiologic data that we were able to collect as well. So that's forthcoming. In terms of next steps, hoping to continue this software development partnership and expand this experience to really hit all of those markers that patients and clinicians have told us would be so helpful. Also, we have applied for a multi-site feasibility trial to sort of bring this to a few other hospital settings and make sure that it really is helpful across clinical sites and isn't something that's just tailored to our setting. So some of the planned features, we do want to have a coping library. So if a kid is sort of feeling stressed in the situation, they can go to the library, they can access some of the coping strategies that they have worked on in their therapy sessions, remember how to use those, practice them, use them to get through the school situation. And as I mentioned, we want it to be responsive to the physiologic monitoring. So if a kid is seeming really stressed, there are some reactions that can happen. And ultimately, it would be great if clinicians can really interact with kids within the simulation so that they're inhabiting other characters and can sort of do their treatment through that level of reality. This is what we hope our feasibility trial will look like. Again, 3 sites, testing this out and continuing to advance the actual software piece of this so that we can integrate all of those pieces. So that's out under review at the moment. Hopefully, we'll get some more support and can keep moving forward. Just a last word, if you're interested in our Innovate Pain Consortium, we do actually have a talk on Friday. We've been trying to move toward dissemination and involving more people who are out there doing this kind of work. So we have a panel of different kinds of clinicians who use VR in pediatric medical settings, and they're going to talk about a variety of challenges that they've faced trying to use VR, as well as some of their successes. So it should be a fairly interesting hour if you're free. And that is what I've got. Thank you.
Thank you, Deirdre. So next up, because every Nano Summit should be closed with a little bit of a discussion about opera, we'll have Jay Scheib, and then we'll take the questions. So please hold your questions. We'll take those with Deirdre and Jay at the end. Okay.
Hi, thanks for having me. So augmenting opera, Parsifal. One might ask why you would need to augment opera, because opera tends to be augmented music already. But in this particular case, I was invited to direct Richard Wagner's opera Parsifal at the Bayreuth Festival last summer, actually before COVID, and then it was postponed, and it premiered this past summer. One of the challenges in making it was that Katharina Wagner, the great-great-granddaughter of Richard Wagner, asked me if I thought we could integrate VR or maybe AR into the performance. This being one of the most important opera festivals, but strictly for the music of Wagner, and known for its very, very special acoustics. And so basically when Wagner first designed this theater, he designed it with an orchestra pit. So the orchestra would effectively be hidden. Whereas in previous or other opera houses of the time, the orchestra was visible. He referred to this as the machine of the music. And he chose to try to hide the machinery that would produce the music in order to create a more immersive experience for the audience. And he designed this strange curve over the pit. So you literally can't see the conductor, can't see light from the orchestra pit. And then duplicated the proscenium out and into the house. So you would really begin to feel, if you're sitting in the theater, as though you were almost on stage, even though you aren't. And so the NCSoft MIT.nano Immersion Lab gaming program sort of gave us the opportunity to take a really big, scary leap at trying to do something which seemed, at least at the time, relatively not doable. So we set out to incorporate AR into into the performance of Parsifal. We made a digital scan of the entire space and built a digital twin of the theater in order to try to figure out if we could place individual headsets, AR headsets, in particular seats in order to give them all the sort of correct perspective throughout the performance. This took it was a nightmare that turned into less of a nightmare. We ended up working with on the Android platform in a Unity environment and chose the Nreal headset, which I think now is called Xreal. The reasons for that are various, but basically some of the other headsets were too expensive and would mess with people's hairdos because an actual good frisure is important at the opening of an opera. We used a WebSocket-based control system. Eventually, that's what we arrived at, because we needed to be able to cue each headset to basically within milliseconds of one another, right? And so we used the Nreal headset. Boom. A hole bigger than the thing the hole is in. The opera Parsifal concerns itself with a wound. There's a king, a guy, Amfortas, who is suffering from a wound that will never heal. Parsifal shows up, the sort of holy fool, basically the dummy who asks the obvious questions, and heals, is able to sort of find the solution that would heal it. So it's the sort of Parsifal story takes place at a time when myth and magic and sort of mythical things are still somehow possible. The sort of magic of pre-Christianity, early sort of unusual rites. And we were coming out of COVID, coming after the murder of George Floyd, and we thought, well, and we sort of came up with this idea, a hole bigger than the thing the hole is in, which seemed to be like a phrase that captured our times, and that became the guiding principle for most of our design approaches. And so we began by, developing a lot of like motion graphics and constantly bucking up against the sort of polygon count possible for a headset, bearing in mind that it's a 4-hour opera, right? So it's 4 hours of content. I would make these like crazy drawings, then we would work with our team of folks in order to create 3D animations. So in this particular scene, Wagner, always like writing stage directions that are difficult to produce on stage. A swan flies above the lake. Parsifal shoots it with an arrow. It falls to the ground. And so while we're using kind of like traditional staging in a sense in this particular scene on stage, we're also putting a live virtual swan that was flying past your head in the headset, arrows whizzing by, and coupling it with the scene on stage. So it was actually kind of a wild experience, and you would hear people gasping. Interestingly, only part of the audience wore the headsets. Our original design brief was to actually figure out how to do it with 2,000 headsets. That's a really big logistical challenge, right? So we ended up with only 330. I don't really know why it was 330, but we ended up with 330, partially for financing reasons, but also in order to limit the headsets to an area in the opera house where if things went sideways, it wouldn't destroy the performance, right? Fortunately, nothing went sideways, which is unbelievable to me still. Here's the swan on stage, and then the swan was in the air. This is another scene that for the folks who didn't have a headset, this is what they would see, and those with headsets would experience sort of a much bigger environment. And we worked with had four cases in the design process. Atmospherics, so rain, fog, smoke, wind. And then we thought about extending the stage architecture, so expanding the actual design on stage into the audience and out, basically bursting through the walls. Character animations, so we added animals, foxes, plastic bags, because we figured, well, the plastic bags will definitely still be here once civilization is gone. And yeah, there we go. Boom. And then there's just another example. I was asked many, many times, like, why are we even bothering to do this? And I think somehow here at MIT in the theater arts program, we spend a lot of time like looking at various ways by which to extend the experiential possibilities of live performance. That has included the incorporation of media and new media technologies pretty much in any way we can imagine. And we sort of test these things and work on them and work on them. And we kind of like run around with this motto that, well, either we figure out how to like use these tools to better express our contemporary situations, or I don't know, or these tools will just express us, right? And things will just get very flat somehow in the world. And so coaxing bits to speak with atoms is, it's an old Media Lab thing, but it's something that we take quite seriously. And also not so seriously. These are flower people floating through the space, which is a scene in the opera, the Magic Garden, the flower maidens, as it were. So we have flower boys and girls that float through the auditorium. Dunk, dunk. And I have just a very short video. I wonder if I can play it from here. Can I? Maybe you can. Please. 20 seconds. So this was shot with a telephone because we loaded the app also into a phone, and we're just testing some of the materials. Boom. Cool. Oh no, I just started it. Great. So this project was developed by myself and my colleague Joshua Higgison in the theater arts program, and with our friends in MIT.nano. Thank you so much. And yeah, there it is. In the next years, we will continue to develop it. Whether we go with a situation of 2,000 actual headsets in the auditorium remains unclear. We're going to kind of pursue a system by which people can actually bring their own headsets, which I think will be a quite interesting event in Bayreuth. Thank you so much.
Yeah, we're good with time. Vladimir, we can take a couple. We're good on time. Okay, so let's Deirdre, we can come back up. Jay, why don't you step? We'll take a couple questions here. I thought there were some more. Please come on up. Everybody get on stage here. We're at the end of the day. You're the yell out your questions, or sort of. There was one question. We'll take this one. It's for Jay in future.
Yes, I think the answer is absolutely yes. And actually, before we did the AR piece during COVID, we produced a VR version of Siegfried, where you could play Siegfried, and it was a kind of first-person shooter scenario. You could pull the sword out of the thing and on cue stab the dragon. And we showed it in Bayreuth, and people had a ball, actually. Yeah.
Okay, so this one's not for you, Jay.
You can try if you want. So this is very stably our population in adolescent chronic pain. It's also fairly true in adult chronic pain, that the vast majority, at least of healthcare-seeking people suffering from pain, are female. We don't fully understand that. There are genetic issues involved. There may be other layers involved in that in terms of who comes to a pain clinic, but that's who we've got. Lots of sex-based kinds of stuff in pain. And then someone asked about the panel on Friday. I don't know if you can go back to my next to last slide, which had a QR code. If not, if there's some way I can send it to any kind of group of people, I'm happy to do that.
What are the possible generative AI for AR and VR in engaging people with tech? So it's everything from generating environments to making sense of people's interaction. And this is actually, Bruce, thank you for the question. One of the things that we're doing is certainly within the Immersion Lab, and we are in some ways the data, this interface between the data, the hardware, and the human. Right? And that shows up in different ways in art, and shows up in different ways in medicine, it shows up in different ways in sports and health. And so, and certainly there's the technology underpinnings. There's the novel sensors, the novel displays, and certainly compute and algorithms. So looking at both sort of the cross, well, what's the foundational technology and how we use these things to make better use of and better interaction with technology, and then what does it map to these different domains? So that's one of the exciting areas where we're defining these little communities of companies and users that we can talk a lot about healthcare and medicine, a lot about art and entertainment and sports and what have you, and then have a cross-cutting set of enabling tools and technology that raises the water level all around. I think with that, I don't want to keep going. I think we're probably good with the time here. So Jay and Deirdre, thank you again.
Thank you.
And JJ, I know he had to take off, so thank you.
Thank you.